Hey everyone. So in this video, I'd like to say a few more things about the graphs of linear functions. Specifically, I'd like to talk about parallel lines, perpendicular lines, and when lines intersect. And so we talked about graphing linear functions in the previous video, and we said that we can use slope and the vertical intercept to quickly graph a linear function. And so if I have the function f of x is equal to negative 1/4 x, take away 1, we can see this coefficient of our x variable, our input variable. We can see this as the slope of our line. This tells us the steepness of our line. And here we can see this negative 1 as telling us one quick point on our line is this is the vertical intercept. The point where our line crosses the vertical axis. In this case, that's the point 0, negative 1. If I plug in 0 for x, 0 times negative 1/4 gives us 0, and then we take away 1. We get negative 1 out for y. So one point on the graph of our line is this point 0, negative 1. And we can see that our slope, right, it tells us the change in y divided by the change in x. And so that tells us, actually before I really say anything further, I want you to notice that negative 1/4, this is the same as negative 1/4. This is also the same as 1 over negative 4. And so here we can see this negative 1/4 slope as, looking at it as negative 1/4, we can recognize that another point on the graph of our function is this point that I obtained by going down 1 and to the right 4 from our point we see 0, negative 1. And similarly, this point here is also on the graph of our equation, because if I go down 1 and to the right 4 units, if I follow our slope, I land on a point on our graph. And so here we can see that the line that we really want to graph here is this one here that goes through our 3 points. So that's a brief refresher of how we can graph a linear function. And now I just want to say a few words about what it means for lines to be parallel and perpendicular. So two lines are parallel if they never cross. And a word we use for where two lines cross is intersect. So if they never intersect. And so here, maybe just to draw one example of a line, a parallel line to our line given by f of x is equal to negative 1/4 x, take away 1. Well, what would a line look like if it doesn't cross our line here sketched in black? It might look something like this. So that's a rough sketch of a line that might be parallel to our original line given by f of x is equal to negative 1/4 x, take away 1. And you might notice here that really these two lines, they have the same steepness, or they ought to have the same steepness for them not to cross. And so really, for two lines to be parallel, they should have exactly the same slope. Right, so if I have the function, like the one we started with earlier, f of x is equal to negative 1/4 x, take away 1, a parallel line might be negative 1/4 x plus 2. Right, the fact that the slopes are exactly the same and these two are linear functions tells us that these lines are parallel. They will never intersect. So another orientation of two lines that really stands out is when they're perpendicular to one another. So two lines are perpendicular if they meet at a 90-degree angle. Right? So here, roughly speaking, it might look something like this. You can kind of fit a perfect square right into the corner of where they meet. And so it's a little harder to see exactly when two lines are perpendicular. It's less clear, less obvious how their slopes or their steepnesses might relate. If we look at this example, this rough sketch here, we can kind of see that this slope here is negative, and this slope is positive. And so we expect their slopes to be different signs, but that's not enough to say when two slopes are perpendicular. And so here, let me sketch the graph of the function that we had earlier. So f of x is equal to negative 1/4 x, take away 1. So this is a rough sketch of this function. And so if I were to rotate this line 90 degrees, we would end up with a line that's perpendicular to our original graph here. And so here, we know the slope of this line is negative 1/4. Let's rotate this picture here and see how the slope of the new resulting line that would be perpendicular, how that looks. So if I take this and I rotate this 90 degrees, and I look at 2 points on this line that really stand out. One point was supposed to be right here, and one point was supposed to be right here. We can see that really the slope would be to go up 4 units and to the right 1 would make this line perpendicular to our original line. And so here we're saying that the slope of the line perpendicular to f of x is equal to negative 1/4 x take away 1, the example we used earlier in this video. Well, the slope of the line is positive 4/1. And so notice here that these two slopes here look very similar to one another. Really, one's the negative of the other, but not only that, one's the negative reciprocal of the other. And so here, if I have the equation of some linear function, f of x is equal to m1x plus b1, right, just some linear function, and I have another linear function, g of x is equal to m2x plus b2. And so here m1 and b1 are they're just some slope and some vertical intercept, and m2 and b2, they're just a different slope and vertical intercept. These two lines, they're perpendicular if their slopes are negative reciprocals of one another. In other words, if I look at this slope and compare it with this slope, m1 should be equal to negative 1 over m2. That's what it means for these two lines to be perpendicular. And so maybe just to have a very concrete example, if I had f of x is equal to negative 2x plus 1, what does the graph of this equation look like? Well, here we have a vertical intercept of the point 0, 1, and we have a slope of down 2 over 1, down 2 over 1, down 2 over 1. So here we can see the line looks something like this. Right, so this is f of x. And then g of x, if I had it was equal to 1/2 x plus 3. In other words, I have this point here at 0, 3, a slope of up 1 and over 2, up 1 and over 2. We can see that the line looks something like this. And because their slopes are negative reciprocals of one another, we know that they meet perpendicularly. So the last thing I'd like to talk about in this video is the idea of finding where two lines cross one another. In other words, their point of intersection. And so whenever we have two lines that are not parallel, they will cross one another. And usually this point where they cross has some extra significance to the problem if these two functions represent some real-world situation. And so we want to be able to find this point of intersection. And so this point of intersection, if we want to find it, we can do so by setting the two functions equal to one another and solving that equation. Right, that's like saying you're setting the outputs of our two functions equal to one another, and you're sort of asking what value of x, what value of the input makes these two outputs the same value. And so that's going to lead to our point of intersection. And so here I've got two functions, and so I want to find where they intersect. And here maybe I'll just draw a rough picture to sort of give us an idea of what's going on. We've got one function f of x here with the slope of -3 and a vertical intercept of 0, -7. So the graph of this function might look something like this. Just a rough picture here. And then here, if I have my g of x function, well, it's got a slope of 2/5 and a vertical intercept of -1/5. So the function might look something like this. The graph of the function might look something like this, and we're really looking for this point where the two lines cross one another. And we can do this graphically, but here it's also beneficial to be able to do this algebraically. So here what we do is we take our f function, we ask when do the outputs come out to be the same as the output of our g of x function. In other words, right here, this -3x minus 7, that's the output of our f function. And this 2x minus 1 all over 5, that's the output of our g of x function. We're asking what value of x makes these two outputs the same. And so if we solve this equation, we'll find exactly that value of x. We'll find the x-coordinate of this point. So here, to solve this equation, we've got some fraction involved, this denominator of 5 on the right side. Maybe just to make our life simpler, we can multiply both sides of this equation by 5 to undo that division. Right, this is an equation that we're solving. We can multiply any number we want to both sides of this equation, so this is a valid thing to do. And when I take 2x minus 1 and I divide that by 5, and then I multiply it by 5, well, that multiplication and division cancel out. They undo each other, and we're just left with 2x minus 1 on the right. And then we've got -15x minus 35 on the left. And so trying to solve this equation for x, we can add 15x to both sides to get 17x minus 1 on the right, and then just -35 on the left. We could add 1 to both sides of this equation to get that x further to being isolated, closer to being isolated. And so we've got 17x, right? Adding 1 to the right side cancels out with that -1. Adding 1 to the left side would give us -34. And then dividing both sides by 17 gives us x is equal to -2. So here, we see this point of intersection. What we found is that the x-coordinate of that point is -2. But we still need the y-coordinate of that point. We're trying to find where these points overlap, or where these lines overlap. And that requires an x value and a y value. How do I get an x value? Well, our functions, they tell us how to obtain an x value or a y value from an x value. Right, so here if I take my function, my f function, and I input -2 into that function, this is going to give me the corresponding y value for this function. So here this is -3 times -2. Take away 7, we get out +6 minus 7, we get out -1. So that's the y value of this coordinate. And we would get the same thing if we plug -2 into our other function, right? This is supposed to be the point of intersection where the x values and the y values are the same for these two functions. And so let's quickly see that we get the same output. Now this is truly a point of intersection, right? So this is 2 times -2, take away 1 all over 5, right? This is just plugging in -2 into our g function. Well, we get -4 minus 1 over 5. This is -5 over 5, which is -1 like we expected. And so in general, if we want to solve, or if we want to find a point of intersection, what we want to do is we want to solve the equation f of x is equal to g of x. Right, this finds us an x-coordinate for this point of intersection. And then we want to plug that solution back into f or g. And what this does is it finds the y-coordinate. This gives us back the output coordinate. Okay, so I have one last example I'd like to talk about really just to get us more comfortable with this idea of linear functions, as well as to give us more practice in finding the point of intersection of two linear functions. And so here, let's just go through this. I've got a table here giving us the median home values in Mississippi and Hawaii at 2 given years. And so here, if we assume that these home values are changing linearly, there's sort of a constant rate of change between these home values of these 2 different years, let's determine a few things. So the first thing I want to determine is this rate of change. I want to figure out which state has home values that are increasing at a higher rate. Right, and so if we're trying to figure out which home values are increasing at a higher rate, we need to find the rates of change of the home values in these individual states. And so for Mississippi, well, the rate of change of the home values would be the change in value divided by the change in time. Right, so I would take one output value, and then I would take another and find their difference. Right, so that's 71,400 to take away 25,200. So that's going to be the change in the price. But then I really want to look at the rate of change. I want to look at how much the values of the home are changing per year. And so here I'm going to divide it by the change in time, which is 50 years between 1950 and 2000. And so here, this gives us 46,200 divided by 50, and 50 goes into our numerator, goes into clean 924 times. So what is this 924 telling us? Well, it's the change in the value divided by the change in time. And so this is really saying that the values of the home, they're increasing by $924 per year. Okay, well, what about the rate of change of the home values for Hawaii? Well, for Hawaii, what we're going to do is we're going to take, what is this? This is 272,700. We're going to take away 74,400 and divide this by the change in the time. Right, so this comes out to be 198,300 divided by 50, which that comes out to be 3,966. And so this is, again, dollars per year. The median values of the homes are increasing by $3,966 per year in the state of Hawaii. If we're assuming, again, this is a really bold assumption, but if we're assuming that these home values are changing linearly. And so in this case, which state has home values that are increasing at a higher rate? Well, Hawaii does. Okay, so the next part of this problem says, okay, if these trends continue, what would the median home value in Mississippi be in 2010? And so I think the simplest way we can work through this problem is to come up with an equation for the home values in Mississippi. Right, so here, if we talk about the home values in Mississippi, we want a function that tells us the values of the homes. Here maybe I'll write m of t is equal to, and so we need to figure out, we know it's a modeled by a linear function, the values are changing linearly, and so we just need to write an equation in this form. M of t is equal to m times t plus b. So here maybe these aren't the best variables. Maybe we'll only do some defining here. So here let's define our input variable. We want it to represent time, but we don't want to just plug in the value 1,950 to represent 1950, and we don't want to plug in 2,000 to represent the year 2000. It might be simpler if we let our variable represent the number of years after 1950. And so this would mean that t is equal to 0. This corresponds to the year 1950, and the t value of 50 corresponds to the year 2000. And we're interested in the year 2010, and so that would correspond to a t value of 60. So these aren't output values, but these are just saying that here we have a value of t, and these are the corresponding years that we're sort of thinking of. And then here the outputs, maybe I'll use M, capital M, for Mississippi. This should be the median home values. In Mississippi. And so here, this lowercase m, this is the slope, the rate of change of the home values per year. And then here, this b, this should be the initial value, or the Teles's vertical intercept, or in other words, the point where corresponding to an input value of 0. Okay, well, we already figured out the slope. We said that the rate of change of the values of the homes in Mississippi, they were increasing by $924 per year. So we know that we have M of t is equal to 924 t plus b. And so now we just need to figure out this initial value. But again, this initial value is the value, the output corresponding to an input of 0. And here, an input of 0, because of the way we defined this input variable, well, that corresponds to the output when the values of the home in 1950. Right, so this is, here this is value of the homes. It's the output corresponding to an input value of 0. It's an output value corresponding to when we're talking about the year 1950. And so in the year 1950, we have a home value, a median home value of 25,200. So really, our linear function can be expressed as m of t is equal to 924t plus 25,200. And so if we plug in 60 into this function, this will give us the median home value in the year 2010. So this comes out to be 55,440 plus 25,200, or in other words, this is 80,640. And this is telling us that the value of the homes in Mississippi in 2010, the median value is 80,640. Okay, and so the last part of this question asks us to find, it says, if we assume that the linear trend existed before 1950 and continues after the year 2000, we want to figure out when the two states' median house values will be or were equal. We want to figure out when these two states had the same median home value. So we want to find the point of intersection. So we want to take this equation that we have, this function that we have, and we want to set it equal to a function that we can make for the values of the home, the median values of the home in Hawaii. And so, if I let h of t represent the median values of the homes in Hawaii, we already figured out that the rate of change was 3,966. And if we define t in the same way, where t represents a number of years after 1950, well then the initial value would be 74,400. Right, so that's just the median value in the year 1950. If we plug in t is equal to 0, corresponding to the year 1950, that's the output we expect. And so we need to set these two equations equal to one another. So we get 924t plus 25,200 is equal to 3,966t plus 74,400. And now we want to solve this equation for t. And so here, if we subtract 924 t from both sides, well, we still have this 25,200 is equal to, what does this come out to be? This comes out to be 3,042 t plus 74,400. And then what we ought to do is we ought to subtract away 74,400 from both sides. And so on the right side, we still have that 3,042t is equal to, the left side we get negative 49,200. And then dividing both sides by 3,042 gives us that t is, I shouldn't write equals here, this is approximately negative 16.174. So what is this saying? This is saying that when t is equal to negative 16.174, we have the median values of the homes are equal to each other between the two states. And so this is the number of years before, this is the number of years after 1950. And so here this is really describing the year, well, roughly 16 years before 1950, so 1934, just before 1934. And so usually when we're trying to find a point of intersection, we also want to find the output value, the y value, but here the problem just asked us, we want to figure out what year the median values of the homes were. If we find the output values, we're finding the median values that were the same, the values of the homes when the two values were the same, but here we just want to figure out the years in which the two values were the same. So we only need to find this value t here for this problem.